Okay, good morning, good afternoon, good evening, maybe even happy middle of the night, Year 12s. Thank you very much for taking the time to come and have a look at this video. As I've explained in class, I expect you to watch this video through and make notes. Feel free to pause, rewind and watch it as many times as you need to in order to make sure you get a decent set of notes from this video. The idea is that in class we will then be practicing lots of practice questions, lots of applying knowledge you gain from this video. I will also at various points be asking you to either pause or to take part in a poll, just in order to make sure that you're interacting with the video. And I'm going to start by asking you, which one is heavier, a kilogram of feathers or a kilogram of lead? And why? Please pause the video while you think about your answer. So the answer, of course, is that they both have exactly the same mass, 1 kilogram. This is the classic trick physics question. The reason is that the mass equals the amount of substance. It's measured in kilograms, and it tells you how many particles you have, not what they weigh. If we wanted to change the weight of something, we could go to a different planet or somewhere else in space where the gravity is different, but we will always have the same mass. The reason, of course, people get tricked up by this is that the volume will be completely different. So how can two things have completely different volumes but have the same mass? The answer, of course, is density. Now, density is a measure of how much mass is contained in any given unit volume. What that means is it's how heavy something is in grams or kilograms for 1 unit volume in centimetres cubed or metres cubed of the material. In other words, it's a measure of how closely packed the atoms, particles, molecules are inside the material. So at this point I'm going to ask you to vote. Which box do you think has the highest volume? Okay, thank you for voting. The answer, of course, is box A. It has a far greater number of particles in the same amount of volume. Therefore, the density of box A will be much higher. Now, in physics terms, density equals mass divided by volume. Written on a formula sheet, you'll often see this as rho equals m divided by capital V. That's curly p equals m divided by capital V. And the preferred SI units for these, mass is measured in kilograms, volume is measured in meters cubed, so therefore, what do you think the units will be of density? Please pause the video and think about your answer. Okay, so if mass is measured in kilograms and volume is measured in meters cubed, the units of density will, of course, be kilograms divided by meters cubed, or generally written as kilograms meters to the -3. Now, just a little warning here. In physics, kilograms meters to the -3 are the preferred units for density. But in many everyday values, and also in the field of chemistry, your units will be used as grams per centimetre cubed. Now, in order to avoid getting the standard form wrong, and therefore getting your answer wrong, there are 2 things you therefore need to be able to do. The first one is to convert from grams to kilograms, and vice versa. And the second one is to convert from centimetres cubed to metres cubed. Now the first one, kilograms and grams, should be relatively simple. 1 kilogram is 1,000 grams, so therefore that's 10 to the 3 grams. Equally, 1 gram is 0.001 kilograms, which in standard form is, of course, 10 to the -3 kilograms. So that one's quite simple. However, converting from centimetres cubed to metres cubed trips a lot of people up. Volume definitely is slightly trickier. For example, there are 100 centimetres in 1 metre. So, 1 metre cubed is 100 times 100 times 100 centimetres cubed. That's 10 to the 6 centimetres cubed. What, therefore, would 1 centimetre cubed be in metres cubed in standard form? If 1 metre cubed is 10 to the 6 centimetres cubed, 1 centimetre cubed is, of course, 10 to the -6 metres cubed. Well done if you got that right. One final warning on units, and that's using litres and metres cubed. This trips a lot of people up. There are 1,000 millilitres in a litre. 1 millilitre is equivalent to 1 centimetre cubed. Note that difference. 1 millilitre is equivalent to 1 centimetre cubed. And 1 litre is 1,000 centimetres cubed. So, there are 1,000 litres in 1 metre cubed, If we combine these two things together, we find that 1 metre cubed is 10 to the 6 centimetres cubed, or 10 to the 6 millilitres cubed, because centimetres cubed and millilitres cubed are equivalent. This does trip a lot of people up. We really need to make sure that you know these relationships. One other thing we need to be able to do to calculate density, and that is measure volumes. Now, for regular solids, there are standard equations that tell us the volume of the solid. So for a sphere, volume equals 4/3 pi r cubed. For a cylinder, volume equals pi r squared h, h being height. You might see this written as pi r squared L, where L is length. And for a cuboid, volume equals height times depth times width. Or you might see it written as length times depth times width. Now, these are relatively simple equations to use, and the one thing that trips people up is that sometimes you are given the diameter of a sphere or a cylinder. You need to remember that diameter is 2 lots of the radius, so you'll need to convert to radius before you plug your radius into your equation. Slightly trickier are irregular solids. Now, these are solids where we can't simply measure or calculate the volume because they don't have standard dimensions. However, we can use Archimedes' principle and the displacement can. Archimedes' principle was that the volume of water that an object displaces is equal to the volume of the object. And this is because water has a density of 1,000 kilograms per metre cubed. So to work out the volume of an object that we can't simply measure, we lower the object into a brimmed can, and we measure the volume of displaced water. The volume of that displaced water tells us the volume of the object we put in the can. Okay, one final thing for density, and that is alloys. Alloys are mixtures of two metals. For example, brass contains copper and zinc in a relative proportion of 60 to 40. Many statues and pieces of jewellery are made of brass because it's got good properties for these kind of things. Now, if we have a volume V of the total alloy, which is made up of two metals A and B, then VA is going to give me the volume of metal A. So the mass of A in that alloy is going to be the density of A times the volume of A. Similarly, the volume of B in the alloy is going to be the mass of B. The volume of B in the metal is going to be VB. So the mass of metal B is going to be the density of B times the volume of B. Now we can use something called the rule of mixtures, which will tell me that the total mass of my object will be the mass of A in the object plus the mass of B in the object. I can substitute in these two equations up here to this equation to get the total mass is equal to the density of A times the volume of A plus the density of B times the volume of B. Therefore, the density of that alloy is going to be the total mass divided by the total volume. So it's going to be the density of A times the volume of A plus the density of B times the volume of B divided by the total volume of the object. And that's the one final equation that you need and you should have recorded by now. Just one final thing I'd like to leave you with, and I'd like you to think about this in the run-up to our lesson next Tuesday. I have got two balloons suspended from a straw and pivoting around a central point. I then popped one of the balloons, and you can see that the balance is no longer balanced. It pulls down towards the balloon that hasn't been popped. My question is, what does this demo show us, and how could we use this demo to estimate the mass? How could we use this demo to estimate the density of the air in the balloon? Please think about that, and I will see you next Tuesday for our first lesson on density.